Today, we are going to be talking about enzyme regulation. Enzymes help catalyze biological reactions, but the kinetics or reaction rates need to be controlled in order to be most effective. Think about each cell as a type of factory that contains the raw materials needed to produce specific products depending on the type of cell. Enzymes would be considered the machines that facilitate these transformation of material to product in a cell. However, no factory operates efficiently if every machine is operating at its maximum rate, because the capability of different machines, like enzymes, differ greatly. Therefore, coordination and regulation of individual enzymes is necessary. The efficiency with which each enzyme operates must be controlled in a way that reflects availability of substrates, utilization of products, and the overall needs of the cell. The first type of enzyme regulation we're going to look at is called feedback control. There's a specific order of the pathway needed to produce the desired final product. In keeping with the factory theme, imagine a candy factory where an assembly line is set up to take material or substrate and turn it into a finished product. The different enzymes in this factory include the machine that drops the chocolates, the conveyor belt, and the worker's hands. The unwrapped chocolate candies are the substrate, which when wrapped will be the final product. If the first enzyme, the machine that drops the chocolate, is running too slow, then no matter how fast enzymes 2, the conveyor belt, and 3, the worker's hands go, they are slow to produce product. In this case, when the factory manager comes out and sees the worker sitting, waiting for another chocolate to wrap, she takes this as feedback that enzyme 1 needs to speed up or activate production. But now that enzyme 1 has sped up, it's working at a little faster pace than the worker's hands can process. Instead of letting the manager see that she can't wrap all these chocolates fast enough, she decides to take the one she couldn't get to and eat them to hide the evidence. When the manager comes out again, she only sees the finished product, but still not a lot of it, so she takes this as feedback that maybe enzyme 2 could be faster. She tells enzyme 2 to speed up and send the chocolates out faster. This time, the worker is in way over her head. She has interrupted the feedback loop, and now, instead of the factory running smoothly, there's a backup of intermediates and incomplete final product. This is clearly inefficient. So for feedback control to work properly, her output needs to be closely monitored by the manager, who can then signal back to enzymes 1 and or 2 to inhibit or slow down production. This type of feedback control in real life can prevent the backup of intermediates, which might have undesired effects on metabolism. Although this was a very simple form of feedback control, many metabolic situations require far more complex patterns of control involving both activation and inhibition. The second type and far more simple form of enzyme regulation we are going to discuss is called substrate-level control. Here we have some green enzymes floating around with purple substrate in a solution. It starts like most normal reactions we expect, where the enzyme converts substrate into product. However, in this case, there's a form of competitive inhibition going on, where the enzyme has the ability to interact with both the substrate and the product. With the substrate level control, product inhibition prevents additional product from being formed from the substrate. In other words, some of the product blocks the enzyme active site, so substrate is unable to bind. In a real-life example, this type of regulation happens during the first step of the glycolytic pathway, which is the phosphorylation of glucose to yield glucose 6-phosphate, or G6P. The enzyme hexokinase can be inhibited by its product G6P. Some enzymes have a set of unique properties that set them apart and include some of our key metabolic regulators. These are often given the name allosteric enzymes. The term allosteric comes from Greek roots meaning other structure or other shape. Pretty much all cases of non-competitive inhibition are forms of allosteric regulation. An allosteric enzyme is a multi-subunit protein with multiple active sites whose activity is affected by the binding of an effector to someplace other than the active site. These enzymes undergo conformational changes, and in the T or tense state, it has a low affinity for substrate, and in the R or relaxed state, its affinity is increased. When an enzyme binds substrate cooperatively, the binding of the first substrate at an active site stimulates the enzyme to stay in R state. This will increase the affinity of additional active sites, promoting additional substrate binding. This increased activity allows the enzyme to increase its catalytic properties. The reason this is considered allosteric regulation is because the homoallosteric effect of the substrate changes active sites far from its binding site by increasing their affinity. However, the biggest advantage of allosteric control may be found in the role of heteroallosteric effectors, which can either be inhibitors or activators. This activation and inhibition of enzymes by allosteric effectors are the keys to the kind of complex feedback control discussed previously. If an enzyme can exist in two conformational shapes, both T and R, that are dramatically different in the strength at which substrate can bind, then its kinetics can be controlled by altering the T state to R state equilibrium. When an allosteric inhibitor binds to an enzyme, this causes a conformational change in which all active sites on the protein subunits are affected, so they either become less effective or don't work at all. These allosteric inhibitors shift the equilibrium towards the T state, whereas allosteric activators shift the equilibrium towards the R state. Some enzymes are regulated by multiple inhibitors and activators, allowing for very precise and complex patterns of metabolic control.